Hello everyone. This time we're going to talk about the finite element method, but we're going to get to it from a different approach. This approach is called the stationary functional approach. If you've seen the previous lectures, we used to derive the finite element model, getting the element equations using what we called what we called weighted residual methods. In specific, we use the Galerkin method. Here we're going to get the same model, but using a different approach, which is called the stationary functional approach. Before we get to talk about the stationary functional approach, I would like to define a few things. These are oversimplified versions, so if you meet someone and tells you this is not the precise definition, well, tell them, okay, yes, it's not the precise definition, it's just a simplified one to get us through the problem. However, if you want more detailed and more specific definitions, you can find them in any textbook about finite element method. The first thing we would like to define in our lecture is a functional. What is a functional? A functional can be defined very simply as a function of functions. This function of functions in mechanics problems is usually the total energy functional. If you remember, the total energy function in mechanics contains the potential energy and the kinetic energy. Also, we include the external work done on structure. So the functional here becomes the energy, and as you remember, energy is a state of the system, so it's defined by a single scalar number. In a simple mathematical way, we would say that the functional I, which is in our case, if we're talking about the mechanics, it would be the total energy, is a function of different functions of the independent variables. This function or this functional is obtained by integrating over the domain a certain combination of those functions. So, for example, if we are talking about total energy, this combination would be the strain energy, the kinetic energy, and the work done. Also, the domain would be restricted to dx, dy, dz, the three physical dimensions, or the three spatial dimensions that we are used to in classical mechanics. This integration over the domain of the potential energy, the kinetic energy, and the external work done will give us a single number, which we'll call the total energy. So the functional here is a single scalar number. Okay. A second definition, or another thing that we will need to define, is the variation. Variation it can be very simply described as a differentiation of the functional. Okay, so if you have a function of functions, then the differentiation would be differentiating this functional with respect to each of the functions that constitute it. Of course, again, this is an oversimplified definition. You'll find a lot of very interesting books that talk about variational methods, but we are not interested in getting into the details right now. So simply, the variation is presented by this delta. When this delta precedes a functional, we say that the functional is being we're describing the variation of this function, of this functional with respect to its constitutive functions. So in that case, since it's a linear operator, we just differentiate the G. Remember here from the previous slide, G is what's being integrated. So we're going to differentiate, we're going to use the chain rule to differentiate G with respect to each of these functions. So you get this relation dg by df times the variation of f. Let's again talk about our mechanics of material example. If, for example, here F1 is the potential energy. So the potential energy is usually the stress times the strain, or the elastic potential energy is the stress times the strain. So differentiating this with respect to the variables included, which generally would be the strain, because the stress can be presented as strain times the stiffness. We get such an expression. Don't worry if these things are not so clear right now. We're going to have an example on a beam and a bar as we go on, and I hope that the examples will make it clear. So anyway, back to what is variation. Variation is in a very simple definition, the differentiation of the functional with respect to its functions. Okay. Just a note before we leave this, the variation of a function with respect to independent variables is always zero, because the functional is not function of the independent variables. Since we integrate here on the right hand side, since we integrate with respect to independent variables, they are lost. This is an integration over the domain, so you end up with a number, not x, y, and z. Okay, so it cannot be. You cannot find the variation of the functional with respect to the independent variables. However, you can find it with respect to the functions. Okay. Now, if we're going to introduce the strain energy and the total energy, let's just remind ourselves with the expression for the strain energy. The strain energy of an elastic structure would be the integration over the volume of the structure of half the stress times the strain. So this would be the general definition of the strain energy stored in any given elastic structure. Notice that using the constitutive relations, we can always remove the stress or the strain and represent it with in terms of the other. So, for example, if we're talking about simple one-dimensional structure, the stress would be the modulus of elasticity times the strain. So this term becomes half E epsilon squared. Or we can say that the strain is equal to the stress over the modulus of elasticity, so it becomes half stress squared over the modulus of elasticity. It doesn't matter in the finite element analysis, we usually use the strain squared representation. In the following videos, we're going to use the above defined terms to derive the finite element model for a bar and a beam. So I hope that when we go through those two examples, what we've just defined here would be clearer.